Hello, everybody. Today we are going to talk about a new chapter, but in this new chapter, actually, we are going to talk about two sections from the previous chapter, chapter 4. Today we are going to talk about chapter 8, which is linear transformations. And then we are going to include the last two sections of chapter 4 in this chapter, because we are talking about the same subject, which is linear transformations. Well, let me start here by a simple thing you already know. All of you know functions and domains and range. So when you have a subset of the real numbers and you have a function or two subsets and you have a function between them, so here is a function f, and here you know domain, we call this domain, and we call this range. By the way, I can ask you here to remind me, what do we mean by a function? Do you still remember that? A function is a relationship between two sets, one of them domain and the other is range, such that each element in the domain is related to exactly one element in the range. In case you forgot that, you better go back and recall the definition of a function. Well, here, our sets, they were subsets of the real numbers. But now, after talking about vector spaces, we can ask the same question here. Well, let's take here a vector space, V with addition and scalar multiplication, and take here another vector space. Let's call it U. And now think about establishing certain relation between those two vector spaces. Well, if we define a function between this vector space and this vector space, it is a function, but from now on we are going to call that a transformation. So transformation. So what do we mean by transformation? Basically, it's a function between two vector spaces. Okay? So that is what we mean by transformation. Okay? It's a function between two vector spaces. Well, now we want it linear. Not only just a transformation, we want it linear. So here, let me write that as a formal definition now. A linear transformation is a function between two vector spaces, such that two conditions are satisfied. Condition number one, we want a linear transformation T is a function between two vector spaces such that T of V1 plus V2 is T V1 plus T V2, and 2, T KV is KTV. Those two conditions, they must be satisfied for all vectors in the domain of your function, and this condition must be satisfied for all vectors in the domain of your function and for all real numbers K. Now, simply we are talking about a function that satisfies those two conditions. So now all we need is just to think about how to check whether a function between two vector spaces is linear or not, how to give examples about linear transformations, and after those examples we are going to find it is just a piece of cake. Okay? So let's here try to see some examples. And again, let me start here by something simple. I want to define a function from R2 to R2 as follows. You take a vector from R2, let's say x and y, and you send this to, I want to take here negative x and y. Well, we can think about this in a geometric way. In a geometric way, what are we doing here? So I'm taking here a vector, let's say v equals xi plus yj. And now I am sending this into negative xy, which means I am sending this to this vector negative xi plus yj. So here, this function does the following. It takes a vector from the right side of the plane and sends that to its reflection on the left side of the plane, and the other way around. Okay? So from a geometric point of view here, this is clear what we mean by this function. Now, the question is this a linear transformation? Well, obviously it is a transformation because it's from this vector space to this vector space. Now, is it linear? Well, we need to check those two conditions. Okay? So here, T is linear. T is linear. Why? Because, well, let's take two vectors in R2. Let me take this vector xy, and let me take this vector AB. Those two vectors are in R2. Well, we can add them and say this is T of x plus A, y plus B. Now, we apply this formula. This formula, it tells you take the reflection, which means here you get negative x plus A, y plus B, this vector. Okay? Well, look at this. I can again here distribute this and say this is negative x, y plus negative A, B. Well, what is this? This is actually, it is T of xy. And what is this? This is T of A, B. So here I am taking two vectors, V1 and V2, and we are finding that we are getting TV1 plus TV2. So this condition, we checked that, it is valid, done. Let's move to the second condition. Well, again, so this is condition number 1, and here condition number 2. T of K multiplied by vector in R2, xy. Again here, this is T, kx, ky, and that is negative kx, ky, and this is, well, take k out, that is k negative xy, and this is kt of xy. So TKV is the same as KTV. Here it is. Okay, so basically those two conditions are satisfied, and now we can say this is a linear transformation. Look here, it's very simple. All you need here is to learn how to write this in a formal way. Okay, how to check those two conditions in a formal way. All right, this is our first simple example. Let's talk about another example. So this is examples. Here started with example 1. Here example 2. Let's define this function or this transformation from M2 by 2, the vector space of 2 by 2 matrices, to the vector space R, as follows. You take a matrix and the image of this matrix is the trace of A. Look, our matrix here belongs to the vector space M2 by 2. And when you take the trace is a real number. So basically this is in the vector space R. Okay? Now, is T a linear transformation? That's the question here. Well, again, since it's a function between two vector spaces, then for sure it's a transformation. Now, is it linear? Well, we need to check those two conditions. Well, I'm sure you still remember the properties of the trace. So here 1, T of A plus B. Now, A belongs to M2 by 2. B belongs to M2 by 2. Okay? So here you are going to get trace of A plus B. But you remember from the trace of the sum is the sum of the traces. Okay? So that is going to be trace A plus trace B. Again here, I am using a property from the trace. When we talked about the trace in chapter 2, we talked about this property. The trace of the sum is the sum of the trace. Okay? Number 2, T, K, A. That is trace K, A. Now, you have a matrix. By the way, I'm talking about 2 by 2 matrices, but you can generalize that into any square matrix. 3 by 3, n by n, whatever you like here. Okay? So when you have a matrix and you multiply that matrix by scalar k, well, what happens to the trace? Well, also this is one of the properties we discussed before. This is k trace of A. Now, that is k T of A. And here maybe I should add one more step and say this is T of A plus T of B. So those two conditions are satisfied, and now we can say we have a linear transformation. Well, there are people that don't like to put these as two conditions. They like to combine those in one condition. If you want to do that, you can do it. Okay? So there is nothing wrong if you combine those two in one condition. And from here and here, say T of, let's say here, U plus KV has to be TU plus KTV. If you want to do that, if you want to combine the two conditions in one condition and do that, you can do that. You have the freedom to do that. I personally like to write them in as two conditions, but you can combine that in one condition. Okay? So here is our second example. This is a linear transformation. This is a linear transformation. Well, can we see an example of a transformation that is not linear? Well, let's take this one. So here, example 3. Let's take T from M 2 by 2 to R. You take a matrix in the domain, and the image of that, the determinant of A. So this belongs to the domain, which is the vector space M2 by 2, and the determinant is a real number, so it is in the vector space R. Is T linear transformation? Well, you need to check the two conditions here, or you need to check this condition. Remember, in mathematics, if you want to say something is true, you have to verify it in general. If you want to say something is wrong, you have to give just an example. So here, if you remember the properties of the determinant, is determinant of AB same as determinant of A plus determinant of B? Is this correct? Well, we know in general this is not correct. Is determinant of KA same as K determinant of A? We know also this one is not correct. So here we are not expecting the two conditions to be satisfied. However, instead of saying that in general like this, let's just take a counter example. So the answer here is no, because let's take here A equals 1, 2, 3, 4. This belongs to M2 by 2. And now I want to take K to be 2. So T of 2A is the determinant of 2, 8, 4, 6. And that is 16 minus 24. That is negative 8. and that is not the same as determinant of this matrix. 1, 2, 3, 4. The determinant of this matrix is just -2. Okay? So no, because here is an example where the linearity conditions are not satisfied. So this is not linear transformation. Okay? All right. Let's take some more interesting examples here. Yeah. So this actually, it is 2 squared, the determinant of, no, here. If I want to put this equal, it will be equals 2 exponent 2, because this is 2 by 2 matrix, and this is 2 by 2 determinant of A, which is -2. This is not, this determinant of this is not, oh yes, you're right, this is not 2, but still it is correct, it's not determinant of this. But the condition, it says K TV, so yes, thank you. All right, let's take again this easy example, and I leave it for you here to do it by yourself. I'm going to again take T from, okay, let's make it now from the vector space M3 by 3 to M3 by 3, defined as follows. T of A equals A transpose. So you relate a matrix by its transpose. So your matrix belongs to this vector space, the transpose belongs to this vector space. Well, this is a transformation. Is it linear? Well, you need to check the 2 conditions. I'll leave it for you to do it by yourself because it is very easy. Okay? So here, do it by yourself. Okay, this is example actually not 2, this is 4, and now example 5. If I go back to this example and I change this, instead of 3 by 3, I take it M by N. And I keep this. This vector space should be what? If this is M by N, this should be N by M. And again, ask yourself the same question. Is this a linear transformation? Okay? Again, I'll leave it for you to think about it and answer that question. Okay. Let's take something even more interesting. Related to your calculus experience. I want to define this transformation from the vector space of differentiable functions on R to the vector space of continuous functions on R. So this is a vector space, and this is also a vector space. So here, you take a function that is differentiable, and you differentiate it as you know from calculus 1. T of f equals the derivative of f with respect to x. So, our function or our transformation takes a function from here and differentiate it. Okay? Is T linear? Is T linear? Well, that takes you back to the properties of derivatives here, and you know that this is indeed a linear transformation. The answer is yes, and this is how we show it. Let F and G, or F1 and F2 belong to your vector space C1R, and again let K be a real number. T, now I'm going to combine the two conditions in one shot. So T F1 plus K F2. Well, this tells you have to differentiate. So basically that is the derivative with respect to x, F1x plus F2x, and here there is a K, and obviously from calculus 1 you can distribute the derivative. This is differentiable, so you differentiate and you get here F1 prime of x plus K F2 prime of x. But what is this? This is actually T of F1 plus K T of F2. So the linearity conditions are satisfied, and hence it is a linear transformation. Okay? So I think by now we have enough examples. Some of them kind of obvious, some of them are interesting, but we have enough examples. If we take a linear transformation and we focus on that, that is important remark here. And let me put here 2 lines. Let's say you have a linear transformation, T from a vector space V to a vector space W. Of course, this is a vector space. So here the 0 vector, or the 0 object, here the 0 object is in V. Okay? Now, what can you say about T of the 0 object? Where does it go? Well, let me make it easier here to see what we're talking about. We have a vector space here, V. We have a vector space here, W. And we have a transformation between them. This is our transformation, whatever it is. Mr. 0 is sitting here. So this goes to something here, for sure. It has to go to something here. It goes to what? That is my question. Well, the answer is easy. Always the 0 object here goes to the 0 object here. So always, in any linear transformation, in any linear transformation, we must have t of 0 here equals the 0 here. Now, again here, this 0 is the 0 of V. It is the 0 object of V. This 0 here is the 0 object of W. Okay? So although I say the 0 vector here, they could be different different zeros because they are coming from different vector spaces. But this must be true all the time. Why is that? Can we prove it? Prove. Well, all you need is just to think about the conditions. In particular, you think about this condition. T, K, V has to be K, T, V. Now, if I take this K to be the 0 scalar, what are we going to get? We are going to get 0 scalar multiplied by V, that is going to be the 0 vector here. And here, the 0 scalar multiplied by this, whatever it is, you are going to get the 0 vector of W. Okay? So here, just because of this, we can take K0. In that case, what you have here is the 0 of V, and what you get here is the 0 of W. So this follows from this condition. So from now on, when you have a transformation, right away you have to know the 0 vector here has to go to the 0 vector here. If that is not the case, then it is not linear. Okay? All right, so here are several examples about linear transformations, and here some nice, interesting observation about the 0 vector. Let me now take you back to matrices. Let A be a matrix, let's say in M2 by 3. For example, I can take my matrix A to be 1, 2, 3, 4, 5, 6. Now, since the beginning of this course, we are talking about matrices, and we're saying, well, matrices, you can think about them as an Excel sheet where you can arrange numbers or arrange data. Now, we want to think about it from a different perspective. When you have a matrix like this, and you want to multiply this matrix by a vector. So here 1, 2, 3, 4, 5, 6. This vector, this is 2 by 3. This vector has to be 3 by 1. So this belongs to the vector space R3. Now, when you multiply, what do you get? Well, let's say here, A, B, C, or X, Y, Z. When you multiply, what do you get? You get a vector here, and that is 1x plus 2y plus 3z. Here it is, x plus 2y plus 3z. And this is 4x plus 5y plus 6z. Now, where is this vector? Well, this vector is 2 by 1, so this vector belongs to R2. So now, here is the idea that is new to us. When I have a matrix like this, I can think about this matrix as a function acting on the vector space R3, and the output belongs to the vector space R2. So A belongs to M2 by 3. I can think about it as a function that takes R3 and sends that into R2. Is it correct? Look at it here. You let the matrix act on vectors from R3. The output will be a vector in R2. So now, instead of thinking about the matrix as just an Excel sheet, think about it as a machine. This machine takes vectors here, and the output is here. Well, that is very interesting here. So if I talk about it in general, I am talking about A belongs to M, let's say here M by N. Now I want to start thinking about it as a machine or a function that takes Rn and sends that into something in Rm. That is the reason here, the last two sections of chapter 4, we put them under this chapter, linear transformations, because it talks about matrix transformations. So here our matrix, we can think about it now as a transformation from this vector space to this vector space. The question is A linear? Now, if you want to use instead of A, T, that's fine. So, I mean, you can say here, my A is T of A. What does that mean? It means I am taking this matrix, and now I am thinking about it as a transformation. So, if you have some knowledge in physics, they talk about electrons as sometimes a wave and sometimes a particle. But still they are talking about the same thing, okay? So it depends whether you are using here relativity or using quantum. You can talk about electrons as energy or as particles, or wave or particle. So here when we have a matrix, we can think about it as a transformation, or we can think about it as just an Excel sheet where you have data stored there. Well, let's answer the question here. Is A linear? Well, check the two conditions and see what happens. I'm talking about the general case. So here, since it's the same, so let me talk about the general case rather than just about this specific case. Okay, so let V1 equals this vector, x1, x2, xn. And V2 and V2 equals y1, y2, yn. So those are vectors in Rn. what happens when I take A, V1 plus V2? Well, you know the properties of matrix multiplication. This is the same as AV1 plus AV2. And that is exactly what we need in condition number 1. Okay? Now, condition number 2, A, let's say here K, V1. That is going to be what? Well, this is now a vector, and this is a matrix. And again, from matrix multiplication, you know that you can take this K out, and this is a V1. Okay? So the two conditions now, the linearity conditions are satisfied now, and in this case, we say hence A equals TA is a linear transformation. So from now on, we can think about matrices as linear transformations. Okay? So whenever we talk about a linear transformation, you can think about matrices as linear transformation. Or when I have a matrix, I have now the freedom to think about it as a linear transformation, or I have the freedom just to talk about it as an Excel sheet where you store some data there. Okay? All right. Let's take here a specific example and see something about the domain and something about the range. Okay, so here is another example. I don't know what's the number of this example. Let A equals 1, 2, 3. This is 2, 4, 6. So this is a 2 by 3 matrix. So here's my question. What is the domain? Now, think about A. Think about A as a linear transformation. 1, what is the domain of TA? 2, what is the range of TA? Okay? Well, the domain of TA is obvious. I already answered that here. So the domain is, here the answer to number 1. The domain is R3. Here it is, Rn to Rm. So here we have 3 columns, so the domain is R3. Now what about the range? That is not obvious. Range. Well, we know TA will take vectors in R3 and sends them into vectors in R2, as we did here. But the question is, okay, are you going to cover, so here is the domain, here is the range, and here is your transformation. Well, how much you cover here? That is the question. That will be your range. Okay? So maybe you don't cover all of R2. Maybe you cover some of it. Okay? So that's the reason here answering the range is not obvious. You need to do some work to see what's going on. Okay? All right, so let me here make it clear. So here you have R3, and here you have R2. Now, you take a vector here, x, y, z, and you send this to what? You multiply A by this vector. Let me call this capital X. You multiply A by X, and here you get what? You get 1x plus 2y plus 3z, and here you get 2x plus 4y plus 6z. This here belongs to this. X plus 2y plus 3z, and this is 2x plus 4y plus 6z. How much you can cover here? Are you going to cover all vectors in R2? Or you are going to cover some of that? That is our question here. Well, I'm going to do it using kind of elementary way, using kind of pre-calculus ideas, okay? And later on, we are going to handle it in a more sophisticated way. Well, I want to think here about which vectors in R2 are going to be covered by this, which means if I take here a vector in R2, let's say AB, and here I take x plus 2y plus 3z, and here 2x plus 4y plus 6z. This equals this. We want this to be this. So what do we have here? We have a linear system if you think about it. We have x plus 2y plus 3z equals A, and here 2x plus 4y plus 6z equals B. We have a linear system. And you want to see here for which values of A and B you can find vectors in the domain of the form x, y, z such that this equals this. Okay? So in other words, if I take here a vector, let's say here 1, 2. Can I find a vector here x, y, z that goes to this vector? Do we have something like this goes to this one? That's the question. Well, from here, you can observe that this, if you multiply this by 2, you get this one. So basically from here, you are going to see that 2A must be the same as B. or B over 2 must be the same as A. What does that mean? It means the vectors that you can cover here should be of this form. So here your range is going to be all vectors in R2 that are of the form A, and if that is A, then B is 2A. And that is going to be span of 1, 2. So are you going to cover all of R2 or a subspace of R2? Well, you are covering a subspace of R2, and this subspace has dimension 1. Okay? This has dimension 1. So the range, here is the important remark, the range is a subspace of R2, and that subspace has dimension 1. Okay, since I'm talking about this, before I erase, let me here talk about the zero vector. We know that the zero vector here goes to the zero vector here. That is for sure. We already proved that. The question is, do we have more vectors here that go to this zero vector? So for sure this goes to this. But do we have something else here that also goes to the zero vector? If we want to think about answering this question, then what are we talking about? We are talking about all vectors x, y, z that go to the zero vector here. So it means we are talking about A0, B0. So in this case, what are we going to get? We are going to get the homogeneous system. We are going to get solve the homogeneous system x plus 2y plus 3z equals 0 and 2x plus 4y plus 6z equals 0. Well, in this case, we are talking about a subspace that is formed by the solution of this homogeneous system, which is this actually is this multiplied by 2. So here you have z equals 3 and y equals 3. And in that case, x is negative 2y minus 3z. So here, that is what we call the null space. Null space is going to be all vectors of this form. Z, I'm going to take t2 here. Y, I am going to take t1 here. And x is negative 2 t1 minus 3 t2, such that t1, t2 are real numbers. And this is span of which vectors? T1, so that is negative 2, 1, 0. And here, negative 3, 0, 1. So here, the null space is spanned by those two linearly independent vectors. So this is a basis for the null space here. So here, the null space has dimension 2. Okay? Now, there is something interesting here, which is the theorem that we had about the null space and about the rank of a matrix. Remember, we have rank A plus nullity of A is the dimension of, or the number of columns, correct? And in that case, we have the domain, which is going to be here, the domain is 3. Well, the rank of the matrix, the nullity of the matrix, and that is the dimension of the domain. So, the nullity of this matrix is here. We found it 2. And the rank is 1, and that is 3. So what we had when we talk about rank and nullity, or rank plus nullity equals the number of columns, still this is satisfied here. But now we have to understand it. We have to understand it in a certain way. Well, look at it. When we talk about 3 here, that was the dimension of the domain. So here we are talking about the dimension of the domain. When we talk about the nullity, we are talking about the dimension of the subspace that goes to the 0 vector. And that is called the null space, or for functions or for transformations, we call it the kernel. Okay? Maybe here I should prove that this is indeed a subspace. Okay, I can write that in general rather than just for matrices. Okay, so here we have the nullity, we have the dimension of the domain, and the rank here is the dimension of the range. So now this theorem, or this fact, I can write it here for linear transformations. Let T from V to W be a linear transformation. Rank of T, well, instead of rank, I am going to say here dimension of the range, plus dimension of the null space, or the kernel, null space, equals what? The dimension of the domain. Dimension of the domain. So in this case, we have dimension of V. And in this case, we have the dimension of the kernel. And this is the dimension of the range. Look here, this is the dimension of the range. I mean, it could be not whole of W. It could be sum of W. Okay? All right. One last thing here. Let me clarify this further. I said here the kernel is a subspace of the domain. So when you take all vectors here that are mapped to the 0 vector here, this is indeed a subspace. Let me clarify that, and I'll stop here. So here, fact, let T from V to W be linear transformation. Kernel, I use K-E-R. Kernel T is going to be all vectors V in V such that T of V equals the zero object of W. Is a subspace. It's a subspace of what? It's a subspace of the domain. It's a subspace of V. Okay? So basically we are taking all vectors in the domain that are mapped to the zero object in the range. Well, all you need is just to check the three conditions of a subspace here. Condition number one, is this set empty or non-empty? Well, obviously, we already know that the zero vector of V belongs to this set because T of 0, 0 of V is 0 of W, then OV belongs to kernel T. So this set is not empty. Number two, to check whether this is a subspace or not, we need to make sure it is not empty. We need to take two vectors and show that the sum is also in the same set. And we need to take a vector multiplied by scalar k and show that the result is also here. So basically here, let V1 and V2 inside the kernel. At the end here, we need V1 plus V2 also in the kernel. So how do we guarantee that? How do we get this? Well, all we need here is to use the linearity of T, and we need to use the fact that both V1 and V2 are inside the kernel. So here we get, from this, we get T of V1 equals 0 of W. And from this, we get T V2 equals 0 of W. Now, what happens if I add those two? I get T V1 plus T V2 equals 0 of W. But remember, T is a linear transformation. So from the linearity condition, I can get T V1 plus V2 equals O W, which means V1 plus V2 belongs to the kernel of T, because T of this is this. So this is satisfied, and here we check that. We are left with the third condition, and that is also easy to check. Three, let V belongs to kernel T, and K belongs to R. What do we need? We need to show at the end here that KV also belongs to the kernel. That's what we need at the end. How do we go from here to here? Well, V belongs to the kernel. It means V belongs to the kernel. It means T of V is the zero object of W. Now, if I multiply both sides here by K, T of V equals K O W. Now, again here, we use the linearity, the second condition when we check the linearity of T. In this case, this has to be T, K, V. And this is the zero of W. And from here, we see that KV has to be in the kernel. And in this case, we are done with the third condition. So here, this becomes now an interesting fact. Whenever you have a linear transformation, the kernel or the vectors in the domain that are mapped to the zero vector in the range, okay? So this is a subspace. So here, finally, here is a chart. So here is the kernel. And here is the zero object of W. So this is W, and this is V here. And this, all the vectors here, they go to this. Now, this we need to understand it better. We need to know here this subspace has a dimension, certainly, because it's subspace of V, and the dimension has to be smaller than the dimension of V. So we need to understand it better. I'll leave it for the next section. Now, here we have other vectors that go here. Now, this and this all together, this gives you the range. And here you have the domain. So basically, what are we saying here? We are saying the dimension of the domain is going to be the dimension of this kernel. We are saying the dimension of the range, the dimension of this, plus the dimension of the kernel is the same as the dimension of the domain. So from there, from here, we are saying the dimension of this, the range, plus the dimension of this, the kernel, the vectors that go to the zero vector here, is the same as the dimension of the domain. Okay? So that is the same. That is the same whether you are talking about linear transformations or you are talking about matrices. Okay? And I stop here, and after this, Professor Assam will continue talking basically about properties of linear transformations, and we'll continue from here. Okay, thank you.